All right, so here's what we have. The test overall, this big redox center is going to be on Friday. So today we'll finish up kind of the last of the theory part of it. We've got a lab tomorrow on electrolysis. We've got a lab on Wednesday, which will kind of tie it up like kind of an application of a bunch of loose ends. And then Thursday review of the test is going to be on Friday. So that's kind of the big picture. I tried to stagger those tests so that some of you, I know, have different classes already. You don't have multiple tests on the same day. Okay. So let's chit chat about this electrolysis stuff. So there's a couple of differences between what we call voltaic cells or galvanic cells. So voltaic cells, also called galvanic cells, these are spontaneous, okay? You don't have to have an outside battery source to it. These are going to take place. Like, for example, you have a strip of copper in copper nitrate solution, and you have a strip of zinc in a zinc nitrate solution, and hook that up to a voltmeter, and you have a salt bridge. Okay? And you can figure out what's going to happen. So these are all reduction or oxidation. So on a voltaic or galvanic cell, these are spontaneous. So what do you know the sign of the E naught value is going to be? Positive. So you'd have a positive E naught value. What's going to be the sign of delta G? Negative. Positive or negative? Negative. Okay, so those two together introduce this concept of spontaneity. Okay, now eventually we're going to talk about a value of K later on today. K is going to what we'll call the equilibrium constant. We'll get into that later. So the main point being is that this is also, you can have some Gibbs free energy out of this. Okay, you could use that flow of electricity to do work. Okay, now not a lot. It isn't like, oh, hey, my car won't start. Let me go get some copper and zinc, and I'll put them in the solution, and I'll start my car. Okay. Is there some flow? Yes. Is it enough to really do anything? No. But if you put a whole bunch of them together, then you can do a lot of work, which is how your batteries work. Your batteries work by building a whole bunch of this type of thing. Okay. Now, in contrast to that, you have electrolytic cells. In electrolytic cells, it's just the opposite. Mother Nature isn't liking this option, okay? So this is like pushing something up a hill. You have to put energy into it. So the classic example of this is, let's say, for example, you look at number one, okay? You have aqueous potassium fluoride. So, and I cannot emphasize this enough. The first thing you have to do is figure out what's in the solution, okay? Kids make more mistakes on this because they don't do this step. Now, here's potassium fluoride. It's Kf, potassium is 1 plus, fluoride is 1 minus. That's why it's Kf. So here's what's important that you understand that you start with. You only have 3 things in this beaker, and 3 things only. You've got water molecules, you have potassium ions. You don't have elemental potassium. Hey, you do not have elemental potassium. You don't have elemental fluorine. You have fluoride ion. That's it. Those are the only 3 things that you have. Nothing else. So when you end up with the reaction, with the overall reaction, the reduction, the oxidation, the overall reaction, these are the only 3 things you could potentially have as a reactant. You don't have oxygen, you don't have hydrogen, you don't have hydroxide ions, you don't have hydronium ions, nothing. This is the only thing that you could potentially have as a reactant. If you have anything other than those 3, you have done something horribly wrong. Now, you're going to dump electrodes in here and you're going to hook it up to a battery, okay? This is not going to happen spontaneously. So, here's what you've got. You got to do the oxidation. You got to do the reduction, okay? And remember, Mother Nature will only do what is easiest for Mother Nature to do. That's it, okay? Mother Nature's going, hey, I'm not digging this anyway because I got to have, an outside power source. That in and of itself has annoyed Mother Nature. She's going, okay, if I've got to do this, I'm going to put forth the minimum effort I have to because I'm just annoyed. Okay, so Mother Nature is just not happy at this point. So, look what could potentially happen with the oxidation. So you have potassium ions, you have fluoride ions, and you have the oxidation of water. On the reduction side, you could have potassium, you could have fluoride, and you can have water. Right? That's it. That's it. Not potassium, not fluorine gas, not oxygen, hydrogen, gold, nothing. That's it. Now, let's start with the reduction. You have a reduction chart. Okay? So the reduction, oddly enough, is going to go in this direction. So what that means is that for this thing to even start on the reduction equation, you have to have one of these that are shown as a reactant on the reduction chart. So right away, fluorine is not, the fluoride ion is not even an option, okay, on the reduction side. It's not even an option. There's two reasons. Number one, it's a product on the reduction chart. You're not going to take it. It's already there. The other thing is that you are not going to make a fluoride ion take in an electron and turn into F2 minus. Okay? That dog is not going to hunt because fluoride has 7 valence electrons. This gets it to the magic 8 ball. Okay? It's not going to go and put, oh, no, I actually want 9. Mother Nature goes, no bueno. Okay? You can only have 8. That's the most stable arrangement of those electrons. So this can't happen for any number of reasons. Now, talk about potassium. Potassium is a possibility, and I'll show you why the potassium is a possibility. It's not a good possibility, but it's a possibility. Because if you go down here to the bottom, you can find K plus an electron turning into elemental potassium. This at least is within the realm of possibilities because this is a reduction equation. Cool. But you all have seen what happens when you drop potassium in water. What does it do? Boom. It reacts violently. So even if you did take potassium and make it gain an electron and turn into elemental potassium, it's going to react. As soon as you make it, it's just going to react with the water in a very violent manner. So Mother Nature goes, cool fireworks show. Let's not get there. Now, here's what you have to keep straight. Is the difference between the reduction of water and the oxidation of water. They are two completely different things. Okay? They're two completely different things. On the reduction of water, you have to start with water as a reactant, as a reduction equation. That's why it's called a redox reaction. So you have to pick this one, which is about 1/4 of the way up. Okay, now if you like the over-under game, Mother Nature is going to pick the over versus the potassium, because that's going to be more likely to go in this direction. So the farther up it is, the more likely it is to go in this direction. So on the reduction side, I'm going to have the reduction of water. So I'm going to have 2 H2O plus 2 electrons, and we get H2 plus 2 hydroxide. Now, here's how you remember this from the lab tomorrow. Here's how you can tell that if you have water splitting up into hydrogen and hydroxide. Number one, you're going to make hydrogen gas. You can collect it. If you collected that, you can collect it and put a test tube or a splint in it, and you would hear the pop sound. Okay? Hydrogen generated here is the same hydrogen gas if you take zinc and drop it in hydrochloric acid. If you could collect it, put a flame in it, boop, you'd make the pop sound. Visually, you could put in an indicator. You could use phenolphthalein, and you would see a color change because that would make that electrode produce hydroxide ion. So there's two ways you can tell you're producing hydrogen gas. Collect it, make it pop, look at the solution, see if it turns it basic. Those are your two visual ways to check this. Because it isn't like you can look at it and go, oh yeah, if I scan in close enough, I see little H's on the atoms, and that's how I know it's hydrogen. No. Okay. Now, so we got the reduction side. Now, the oxidation. Could potassium even remotely undergo oxidation? N squared, you shake your head no. Why?
I've never seen K plus 2 before.
Yeah, because if this did this, you would make K2 plus an electron. No, horrible, bad. Not even a possibility.
Well, not yet.
Now, what about fluoride? Is fluoride a possibility?
Definitely.
It is. But where's fluoride on this chart?
It's very, very, very.
Very, very top. Okay? That means this really, 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 I say again, really, wants to go in this direction. And Mother Nature goes, you want me to flip this around? I think not. Okay? But, and if you play the over-under game, down here, and this is what you have to look at, the oxidation of water is when you're going to start with water, okay, and reverse this. So if you come down here, not the oxidation of water, the reduction of water. So if you come down here, where it says 1.33, you can make water undergo this oxidation. But you have to start with water as a product and then flip it, okay? You have to flip it. So the oxidation of water, if you do this, you get 2H2O, yielding O2 plus 4 hydroniums plus 4 electrons. Okay? Now, here's how you can tell if this. You make oxygen gas, which makes stuff burn brighter, okay? Because oxygen is typically a limiting reactant in a reaction. So if you had a burning wood split, it would burn really much brighter if you had the oxygen gas. And you're going to produce hydronium ions, which would make the solution acidic. So basically, you're producing oxygen gas and protons. Okay, literally, that's what you're making. You're making protons. How do we make protons? Make water undergo oxidation, and you're producing protons. Okay. Now, when you combine these together, so water in this situation is both reduced and oxidized, okay? It's both reduced and oxidized, but you have to go through that same process. So come over here. This is 2 electrons. We're going to multiply all of this by 2, and then that becomes 4, that becomes 2, that becomes 4, that becomes 4. Now, when you go through this whole rigmarole, you combine your hydroxides over here. Whoa, that got weird. You combine your hydroxides here with those 4 hydroniums. When you combine hydroniums and hydroxides, what do you get? You make more water. Oh, great, we're going to make more water. We're going to make this. Out of the corner of my eye, that just looks weird. That's all I got to say. So, at the end of the story, here's what you got. You have 2H2O, you'll need 2H2 plus O2. So if water is both reduced and oxidized, basically you take water and you split it up into hydrogen and oxygen. Okay?
And that's hydrogen.
Yes. Now, this takes an input of energy, which is cool. Why is it a good thing that this takes an input of energy? Yeah, because if this was a spontaneous reaction, we wouldn't be here having this discussion. Okay? Now, is this what happens, though, because this takes the input of energy, is this what happens when you boil water?
No,
How do you know?
because You can't light water vapor on
Yeah.
fire.
You can try.
I just like this.
Yeah, it's like, hey, when an explosion boils water, we'll throw a match over the top of it. Boom! Okay? Which would be really cool, don't get me wrong.
Because it's not enough energy. The water vapor is water, it's not actual hydrogen.
So what's happening, allow me to give you a visual. No. Okay, so, and we'll get into this when we get into what's called intermolecular bonds. So basically what happens when you boil water is that here's the two water molecules. You have what we call intra and intermolecular bonds. Intramolecular bonds is what holds the hydrogen and the oxygen together. Okay? Intermolecular bonds are what hold the water molecules together. Now, water has pretty substantial intermolecular bonds. That's what allows water to exist as a liquid. Okay? Oxygen and nitrogen, key components of our atmosphere. We kind of need them. When those run into each other, and this is a horribly non-scientific term, so don't judge me if that's not scientific. I know it's not, but you get the visual. So when nitrogen and oxygen run into each other, make up our atmosphere, they're not sticky. Okay? Which is why we have an atmosphere, which is why we have atmospheric pressure, because they don't run into each other and they don't stick. If they were sticky, we wouldn't have an atmosphere, because then we'd have liquid nitrogen and liquid oxygen. Okay? But water is pretty sticky. So they run into each other, they tend to stick together, which is why we have liquid water. So when you boil water, you break the bonds that hold the water molecules themselves together. This is why water doesn't go boom when you boil it, okay? Because you're breaking these bonds that hold them together. So when you see the little bubbles in the water, those are vapors, those are high energy water molecules. You're not breaking these bonds that hold the hydrogen and the oxygen together. That requires a tremendous amount of energy, much more than just breaking these bonds. So if you've ever heard that old adage, a chain is only as strong as its weakest link. Okay? So when you put energy into a system, you break the weakest bonds first. The weakest bonds are the bonds that hold the water molecules together. If the weakest bonds were what held the hydrogen and oxygen together, then when you boiled water, it would separate into hydrogen and oxygen. Okay, so let me give you a hint. When water is both reduced and oxidized, what you should see if you've done all 10 of those, okay, if you've done all 10 of those, that should happen twice. One of them we just talked about, okay? So you should have a total of 2 where water is both reduced and oxidized, okay? Total of 2. Now, if you look at, like, for example, on number 6 where you have aqueous magnesium sulfide, you can't find sulfide on the chart. So guess what? Don't worry about it. It's not going to happen.
Uh-oh. Don't
Okay.
worry about what.
On that number 6 where you have aqueous magnesium sulfide, it's not going to mess with the sulfide. It's not on the chart. It's not going to happen. Sulfide.
I asked ChatGPT, and it said sulfur is good.
Are you sure it wasn't?
I had to verify. I literally did not know this. It was not on this. And he took like 4 hours to respond.
Oh, that is a bold-faced lie. That, Nathan Nelson, you know that is a bold-faced lie.
It was like 30 minutes. That was pretty fast.
On a Sunday night.
Yeah.
Mr. Burkett, is that question with the sulfite, may that be the other one that?
It might be.
Okay.
What, Big Mike?
So let's say I had 1/2 O2. Don't you just leave that as 1/2 O2?
Where could you possibly get
To be
1/2?
fair, on
That's what-
the note sheet.
Yeah, that's what it
did
says
say
on the
one.
paper.
No, don't have
How
that.
do you even get half?
Don't have that.
No, wouldn't that just be like, oh?
Okay,
I might know.
Oh, what happened?
now, when you get to number 3,
Yeah, what does that mean?
Okay, because this is what we're talking about today. So you have molten aluminum oxide. So here's the story. So aluminum does not exist as aluminum, but we go through a lot of it, right? So aluminum cans, if you want to have the aluminum to make aluminum cans, don't go out and mine pure aluminum. It doesn't exist, okay? You have to get it and separate it because it's bound up with something else, okay? So if from a recycling perspective, this is the cool part about recycling aluminum. Aluminum cans can be recycled again and again and again and again because it's just aluminum. Plastic is tough to recycle because there's so many different types of plastic and those long polymer bonds that make up plastics tend to break down over the period of time. So aluminum is simple to recycle, okay? So what's happening on number 3? Someone has basically given you this sample of aluminum oxide. So here's this big chunk of aluminum oxide. And you want to separate it into the constituent parts of aluminum oxide. So you have to start with this. What's the formula for aluminum oxide? If you don't have that, you are just dead in the water right from the beginning. Al2O3. Okay? Because aluminum is 3+, oxygen is 2-. Do this cross switch like you've done since Chem 1. There's aluminum oxide. Now, so when you heat this stuff up, okay, so you would have this big vat, okay? And you would have, just like any type of cell that involves electricity, you're going to have a cathode, and you're going to have an anode. Okay? Same idea. You're going to have a cathode, you're going to have an anode. Okay? Same thing. Nothing changes. What's going to occur at the anode? Oxidation. And it's the same rule. Okay? You have oxidation happening at the anode. You have, let's get reduction, the red cat, happening at the cathode. You got reduction happening there. Now, here's what you have to understand in terms of making this work. Once you melt this, okay, and it becomes molten, like literally, you have to get this stuff hot enough that it turns into a liquid, okay? Not pliable, not like butter, like you have to make this stuff boil, okay? It makes a tremendous input of energy. But again, you're breaking the bonds that hold the aluminum and the oxygen together. So what's important to understand is that once that turns into molten, then you have aluminum ions and you have O2-. You do not have oxygen gas. You do not have elemental aluminum yet. Okay? You have aluminum ions, you have oxide ions. Okay? So no matter what the molten form is, like for example, you get down on number 8, where you have molten lithium fluoride. That's existing as lithium ions and fluoride ions. So a molten form of anything has the ionic structure, whether it's a cation or an anion. So what's going to be reduced? The aluminum or the oxygen? Aluminum. You're going to force it. So you're going to force this to take electrons. Aluminum's going, dude, I'm more stable without the electrons. Mother Nature goes, suck it up, buttercup. Here's 3 electrons. Deal with it. Okay? And aluminum's going, I don't want to. This is why you have to force this to happen. Now, the oxygen isn't happy either. Because the oxygen's sitting there going, God, come on. I gained 2 electrons. I have a noble gas arrangement. Come on, look at me. I look like Taylor Swift. Come on, this is cool. And Mother Nature goes, nope. And Mother Nature's all about fairness. Mother Nature goes, look, if I want to make the aluminum take 3 electrons, I got to get it from somewhere. Guess what, buttercup? It's you. Okay? So Mother Nature is going to go to the oxygen and go, tough. Take the electrons from you and give it to the aluminum. Nobody's happy about it. The aluminum isn't happy, the oxygen isn't happy. But Mother Nature is about fairness. So Mother Nature goes, I got to take electrons from something. I got to give it to somebody else. And here's the deal. This is what's going to happen. So out of this, you are going to get elemental aluminum, and you're also going to get oxygen gas. So this is what you would see happening. On that reduction side, you would physically see aluminum start to form on that cathode. You would see bubbles of oxygen gas begin to form at the anode. Okay, so this is how you get aluminum to put into your aluminum cans. They heat this stuff up. You have the aluminum, you let it run for a certain amount of time, and then you go in and you scrape this stuff up. Okay, just like I made silver on the lab on Friday. Okay, took silver ions, put it in a solution, boom, hey, I made silver. Same thing is going to happen here with the aluminum. Okay? Now, so the short version of this is that you have aluminum oxide turning into elemental aluminum and O2. Balanced? God, no. Make sure you balance that equation. Okay? Because if not, then you have violated one of the great conservation laws of all chemistry. So, let me give you some hints. Number 10 should have no water. Okay? 9 should have 6 waters. 7 should have dose.
Wait, for 7, can you go over the chloride rule?
Okay, chloride is the one kind of wonky exception to this. Okay, I briefly mentioned that. So, chloride is technically above water. So Mother Nature should pick water, but we think it has to do with some valence electrons and electron shielding. Mother Nature will actually pick chloride over water. Okay, so on number 7, you should have, here's your 2 reactants on number 7. Should be chloride ions and water. Okay? Don't mess with the ammonia. Mother Nature goes, ammonia, you're just a lot, and I'm not going to mess with you. Okay? 5 should have no water. 4 should have 2 waters. And 2 should have 2 waters. Cool with that? Yes, ma'am.
On 5, how are we supposed to know if it goes to CR2 or if it goes to elemental?
It's always going to go to the elemental. So that Br minus is always going to turn all the way to bromine. And the same thing, which one, you asked me one about yesterday. Oh, the chromium 3 plus on number 5, that goes all the way to elemental chromium. So get those handed in. Mark, you stop the camera, please.